Section 20.4, Cell EMF. At this point, you may be asking yourself why electrons flow spontaneously the way that they do. Why do electrons transfer spontaneously from a zinc atom to a copper-2 ion, either directly in reaction to figure 20.3 or through an external circuit, as in the voltaic cell in figure 20.5? In this section, we'll examine the driving force that pushes the electrons through the external circuit in the voltaic cell. In a simple sense, we can compare the electron flow caused by a voltaic cell to the flow of water in a waterfall. Water flows spontaneously over the waterfall because of the difference in potential energy between the top of the falls and the stream below. In a similar fashion, electrons flow from the anode of a voltaic cell to the cathode because of the difference in potential energy. The potential energy of electrons is higher in the anode than it is in the cathode, and they spontaneously flow through an external circuit from the anode to the cathode. The difference in potential energy per electrical charge, the potential difference between two electrodes, is measured in units of volts. 1 volt is the potential difference required to impart a joule of energy to one charge of Coulomb, a charge of 1 Coulomb. The potential difference between the two electrodes of the voltaic cell produces the driving force that pushes electron through the electric external circuit. Therefore, we call this potential difference the electromotive or causing electron motion force, or EMF. The EMF of a cell, denoted capital E sub cell, is also called the cell potential. Because the cell potential is measured in volts, we often refer to it as the cell voltage. For any cell reaction that proceeds spontaneously, such as that in a voltaic cell, the cell potential will be positive. The EMF of a particular voltaic cell depends on the specific reactions that occur at the cathode and anode, the concentrations of reactants and products, and the temperature, which we'll assume to be 25 Celsius unless otherwise noted. In this section, we'll focus on cells that are operated at 25 Celsius under standard conditions. Recall from section 19.5 that standard conditions include 1 molar concentration for reactants and products in solution, and 1 atmosphere pressure for those that are gases. Under standard conditions, the EMF is called the standard EMF, or the standard cell potential, and is denoted E sub naught of the cell. For the zinc-copper voltaic cell in figure 25, for example, the standard cell potential at 25 Celsius is 1.110 volts. Recall that the superscript naught includes the standard state conditions. Standard reduction potentials. The cell potential of a voltaic cell depends on the particular cathode and anode of the half cells involved. We could, in principle, tabulate the standard cell potentials for all possible cathode-anode combinations. However, it is not necessary to undertake this arduous task. Rather, we can assign a standard potential to each individual half cell and then use these half cells to determine the standard potential of the cell. The cell potential is the difference between the two electrode potentials, one associated with the cathode and the other associated with the anode. By convention, the potential associated with each electrode is chosen to be a potential for reduction to occur at that electrode. Thus, standard electrode potentials are tabulated for reduction reactions. They are standard reduction potentials, denoted E naught sub rad. The cell potential, E naught sub cell, is given by the standard reduction potential of the cathode reaction, E naught sub rad cathode, minus the standard reduction potential of the anode reaction, E naught sub rad of the anode. We will discuss equation 20.8 in greater detail shortly. Because every voltaic cell involves two half cells, it's not possible to directly measure the standard reduction potential of a half reaction. However, if we assign a standard reduction potential to a certain reference half reaction, we can then determine the standard reduction potentials of the other half reactions relative to that reference. The reference half reaction is the reduction of hydrogen ion to hydrogen gas under standard conditions, which is assigned a standard reduction potential of exactly 0 volts. An electrode designed to produce this half reaction is called a standard hydrogen electrode. A standard hydrogen electrode consists of a platinum wire connected to a piece of platinum foil covered with a finely divided platinum that serves as an inert surface for the reaction. The electrode is encased in a glass tube so that the hydrogen gas under standard conditions, 1 atmosphere, can bubble over the platinum and the solution containing the hydrogen ions under standard 1 molar conditions. Figure 2010. The standard hydrogen electrode is used as a reference electrode. A standard hydrogen electrode consists of an electrode with finely divided platinum in contact with hydrogen gas at 1 atmosphere and an acidic solution of hydrogen ion at 1 molar. Molecular depiction of the processes that occur in the standard hydrogen electrode. When the standard hydrogen electrode is the cathode of a cell, 2 hydrogen ions accept an electron from the platinum electrode and is reduced to hydrogen atoms. The hydrogen atoms bond together to form hydrogen gas. When the standard hydrogen electrode is the anode of a cell, the reverse process occurs. The hydrogen gas molecule at the surface loses 2 electrons and is oxidized to hydrogen ion. The hydrogen ions in solution are hydrated. Figure 2011 shows a voltaic cell using a standard hydrogen electrode and a standard zinc 2-ion zinc metal electrode. The spontaneous reaction is the one shown in Figure 21, namely the oxidation of zinc and the reduction of hydrogen ion. We make 2 important observations about this cell. The zinc ion zinc metal electrode is the anode, and the standard hydrogen electron is the cathode, and the cell voltage is 0.76 positive volts. By using the defined standard reduction potential of the hydrogen ion, E naught red equals 0, and equation 28, we can determine the standard reduction potential for the zinc ion zinc metal half reaction. Thus, a standard reaction potential of negative 0.76 can be assigned to the reduction of zinc 2 cation to zinc metal. Notice that we write the reaction as a reduction, even though it's running in reverse as an oxidation in the cell in Figure 2011. Whenever we assign a potential to a half reaction, we write the reaction as a reduction. The standard reduction potentials for other half reactions can be established from other cell potentials in a fashion analogous to that used for the zinc ion to the zinc metal half reaction. Table 20.1 lists some standard reduction potentials. A more complete list is found in Appendix E of the textbook. These standard reduction potentials, often called half-cell potentials, can be combined to calculate the EMFs of a large variety of voltaic cells. Because standard potential measures potential energy per electrical charge, standard reduction potentials are intensive properties. Thus, changing the stoichiometric coefficient of a half reaction does not affect the value of the standard reduction potential. For example, the standard reduction potential for a reduction of 2 moles of zinc ion is the same as that for the reduction of 1 mole of zinc ion. We're now in a position to discuss equation 20.8 more fully. For each of the half cells, the standard reduction potential provides a measure of the driving force for reduction to occur. The more positive the value of the standard reduction potential, the greater the driving force for the reduction. In any voltaic cell, the reaction at the cathode has a more positive value of standard reduction potential than does the reaction at the anode. In essence, the greater driving force of the cathode half reaction is used to force the anode reaction to occur in reverse as an oxidation. Equation 20.8 tells us that the cell potential is the difference between the standard reduction potential of the cathode of half reaction and that of the anode half reaction. We can interpret the standard cell reduction as the net driving force that pushes the electron through the external circuit. Equation 20.8 is illustrated graphically in Figure 2012, in which the standard reduction potentials are shown on a scale, with the more positive standard reduction values higher on the scale. In any voltaic cell, the cathode half reaction is the one higher on the scale, and the difference between the 2 standard reduction potentials is the cell potential. Figure 2013 shows the specific values of the standard reduction potential for the zinc-copper voltaic cell in Figure 20.5. Oxidizing and reducing agents. We have thus far used the tabulation for standard reduction potentials as a tool for examining voltaic cells. We can also use the standard reduction potential values as a valuable aid for understanding aqueous reaction chemistry. Recall, for example, the reaction between zinc solid and copper 2 ions, shown in figure 20.3. Zinc plus copper 2 ions yields to zinc 2 ions plus copper solid. Zinc metal is oxidized, and copper ions is reduced in this reaction. Because these substances are in direct contact, however, we are not producing usable electrical work. The direct contact leads, in essence, to a short circuit of the cell. Nevertheless, the driving force for the reaction is the same as that of the voltaic cell in figure 20.5, because the standard reduction potential value for the reduction of copper ions is more positive than the standard reduction value for the reduction of zinc cations. The reduction of copper ions by zinc is a spontaneous process. We could also make equivalent statement for that the oxidation of zinc metal by copper 2 ions is a spontaneous process. We can generalize the relationship, the value of the standard reduction potential, and spontaneity of redox reactions. The more positive the standard reduction potential value for a half reaction, the greater tendency for the reactant of that half reaction to be reduced and therefore to oxidize another species. Examination of the half reactions in Table 20.1 shows that fluoride is the most easily reduced species and is consequently the strongest oxidizing agent listed. Among the most frequently used oxidizing agents are the halogens, oxygens and oxyanions of manganese, chromate, and nitrate, whose central atoms have high positive oxidation states. Notice that in Table 20.1, all of these species undergo reduction with large positive values of standard reduction potential. Lithium ion is the most difficult species to reduce and is therefore the poorest oxidizing agent. The fact that lithium ion is so difficult to reduce tells us that the reverse reaction, the oxidation of lithium solid to lithium ion, is a highly favorable reaction. Lithium metal has a great tendency to transfer electrons to other species. In water, it's the strongest reducing agent among the substances listed in Table 20.1. Commonly used reducing agents include hydrogen gas and active metals such as the alkali metals and the alkaline earth metals. Other metals that have negative standard reduction values for the reduction of the corresponding cations, zinc and iron, for example, are often used as reducing agents. Solutions of reducing agents are difficult to store for extended periods of time because of the ubiquitous presence of oxygen, a good oxidizing agent. For example, developer solutions used in photography are mild reducing agents. They have only a limited shelf life because they're readily oxidized by oxygen in the air. We see that the list of standard reduction values provides an ordering of the ability of substances to act as oxidizing or reducing agents. This relationship is summarized in Figure 2014. The substances that are strong oxidizing agents are reduced to substances that are weak reducing agents and vice versa. This inverse relationship between oxidizing and reducing strength is similar to the inverse relationship between the strengths of conjugate acids and bases. Figure 2014. The standard reduction potentials listed in Table 21 are related to the ability of a substance to serve as an oxidizing or reducing agent. Species on the left side of the half reactions can act as oxidizing agents, and those that are on the right side can serve as reducing agents. As the standard reduction potential becomes more positive, the oxidizing strength of the species on the left increases. As the standard reduction potential becomes more negative, the reducing strength of the species on the right increases.